Hey folks, welcome back. We are getting ready for exam 3. So in this problem we have a hanging frame, as you can see in the lower right, and we are told that the members A, B, and BC are slender rods. The weight of AB is given as 8 pounds, weight of BC is 5 pounds. We're told that there is 6 pounds of tension in cord AC, that the frame itself is hanging and it can rotate about point C. There is a moment imposed upon point C, and we are asked to find the moment is imposed upon member BC, and we are asked to find the angular acceleration of the system and the moment m. So let's get to it. A few things to consider here. First of all, anytime we're in a kinetic system, meaning that we're considering force and rotation, then there's a few things that we're going to know. First of all, we are going to be using the parallel axis theorem. So remember, the parallel axis theorem is that the sum of the moments about some point is equal to I bar plus, this in parentheses, plus mr squared times alpha, right? And we can get around this if we can make our point of rotation coincident with our our point of rotation coincident with our point of analysis, right? So if we are in a constrained plane, then we can get around that. The other thing is that we're going to need this I bar for a slender rod. So I bar for a slender rod that is I bar equals 1/12 ml squared. So when we calculate these, we're going to need it for member AB and BC. So I did that already. So AB is going to be equal to 1/12 times ml squared, and that is, where are we at here? 0.08 2816. Okay, and I bar, not AB, but BC is equal to 1/12 ml squared again, and this time it is 0.02022. I usually keep quite a few digits with me when I'm doing those, just because I'm not sure how many times I'm going to use them. So first things first, where to begin? Well, let's begin with A. So if we look at the system, there's a lot going on with it, but what we need is a point where we can analyze from, where we can get alpha. And this, back to this conversation that I was having with my students, the problems in this chapter 16 are not necessarily difficult, but they do require you to consider how to solve them, right? So there's not many steps, but you need to think carefully ahead of time. So you might stare at a problem for a few minutes just trying to figure out how to solve it. And again, this being a review problem, probably a good idea now that I've given you the second moment of inertia. Go ahead and pause the video, see if you can solve it, and we'll see how you did. So, okay, all right, so the easy way to get the angular acceleration is to analyze bar AB. And if we do that, then we know that the weight is here. Oh, which reminds me, when you start working with assemblies, you're going to have to know where the middle of things are. You just do. So this is TAC. This is the weight of AB. And notice that the moment M is applied to bar BC. So that is not something that we need to consider in this calculation. So let's see, these are in feet, right? It's easier to think of this in feet. So it is 1 foot from here to here. Okay, 1 foot from here to here. Right, so when we do a moment, so we'll say the sum of the moments about B, right, because we want to take into account the tension there, because it's on the rod, that's going to be equal to the sum of their effect, right? So MB effective. All right, so what contributes? And, you know, what's the direction? Well, given the nature of the direction that M is going to rotate things, then that sort of necessarily means that this is going to be our I bar alpha, right? So we'll define this as the positive direction. Okay, so is that right? That doesn't feel right. Yeah, maybe. No, that's backwards. I think it's backwards. Don't know. We'll go with it. All right, so TAC, so that's a 3, 4, 5 triangle, right? So we've got, this is A, C, and then B, so this is 12, and this is 9, so 3, 4, 5, so this is 15, right? So that means that the vertical component that we need is 3/5 of TAC. So 3/5 of TAC is 6 pounds. Okay, and we need the distance. The distance is 2 feet. Okay, and let's see, I'm calling this negative, and plus the weight. The weight is 8, and it is 1 feet away. All right, and that is going to be equal to IAB times alpha. And having just done this problem, I know that alpha is facing the wrong direction. Interesting. Okay, so right, so it's actually going to be the other way. All right, so when we solve this, we get let's see, 3/5 of 12 is 36/5. Plus, 8 minus 36/5. So that is 7.2. So that's 0.8. 0.8. Divided by this guy, and that is 0.082816, right, equals alpha, and no, that's, no, that was, I was right the first time. I just thought it was going to end up the other way. Okay. Then this actually is going to equal 9.66. And this is radians per second squared in this direction. Okay. All right. Now for B. We are going to need to do a moment about C, right? So let's do that. We'll just we'll take the moment about C, and then as we need things, we'll go get them, because there's quite a bit to this calculation. All right. So again, force equals mass times acceleration, and here we're going to be using the parallel axis theorem. So the moments about C. Well, let's see. We have, if we just sketch this, and let me do it with lines, and then I'll just use the dotted line to represent the chord, right? So if this is C, then we have the moment M, which I'll put right here. Right, this is M. And so then what are the other forces? Well, there's the weight here, right? But that's directly below C, so that doesn't matter. There's also the weight here, right? And if this is 1 foot here, then this is 0.5, right? And so there's M, and we'll say that the direction of M is positive, right? So we'll call that plus. So then if that's positive, this is negative, so it's going to be minus 0.5 times the weight of, see, this is B. This is B. And so BC is 5 pounds. All right, and that's going to be equal to the motion of this and this. Well, let's see, what are the motions there? The motions are, we've got this, so for, let's see, it's A here, so this is I, A, B, alpha, right? And then as it rotates, there's also going to be this component, right? And this is the M, A, B, A, A, B. And so with BC, there's this, right? So the I think it's just the alpha, right? Because this is the momentum, right? So this is the alpha, but I'm going to write it the same just so that I'm consistent. So we're sticking with momentum for now. BC alpha, okay, and then there's also this part, right? So this is MBC A BC. and that is a W. This is another W. Okay, lots going on here. All right, so we need the representation of BC and AB. So first things first, AB, and we can just write it in the same way that we've got it up here. We'll say I bar AB plus M, which is the mass, so that for AB is going to be, well, we'll write it algebraically first, MAB, and then R, so we're going to need parentheses here, and the R here is from the axis of rotation to the center of this point. So MAB is right here, and this is 9 inches, so that's 0.75. So 0.75 squared, there, this is going to be times alpha, plus, then we need the contribution from bar BC, so I bar BC plus M, so MBC times, and now they're both sides are 3, 4, 5 triangles, so if you look at it, this is 9, this is 12, which makes this 15, right? But we're looking for the middle, and that would be 7.5, and we want it in feet, so that's 7.5 over 12, and that gives us 0.625. That's going to be squared, and the whole thing is going to be times alpha, right? So we could actually add up all of the internal components and then multiply it times alpha once. Either way is fine. There's it's not more accurate to do it one way or the other, whichever one works. So let's see. As we start adding numbers here, then M is going to be equal to 2.5 plus, okay, IAB is this guy here, so 0.082816 plus M is, in this case MAB is 0.75, so no, R is, M is the mass, so this is 8 divided by 32.2 times 0.75 squared plus, and now we're at IBC, so that is 0.02022 plus, and I'm going to bring it down a line here, so plus, anytime you have multi-line equations, indent a lot so that it's obvious what you're doing. So we got that, and then all we need is this final term, so MBC is 5 over 32.2, and that's going to be times 0.625 squared. Okay, and all of this is going to be times 9.66. Okay, all right, so I calculated this, well, right before I sat down to record this for you, and I got that M is 5.43 foot-pounds, and that is in that direction, right, as you can see from the image right next to me. So the big thing here is notice that even though it got a little intense, really all it was 2-moment calculations. So it's easy to overthink the kinetics problems, but it tends to be that they're not actually as bad as you think. So I would definitely make sure that you include the parallel axis theorem in your notes. I will make sure that on the exam you have the table that gives you the mass moment of inertia, and so you'll be able to look that up, but you'll need to know how to look it up. All right, it's not going to have arrows. What else? Yeah, all right. Well, I hope that was helpful, and I will see you in the next video.